Hello dear students and welcome to my YouTube channel. In this sequence of videos, we are going to study about quadratic forms and the associated matrix transformation. Let us begin with the definition of a quadratic form. So we are going to first talk about what is a quadratic form. So a quadratic form is nothing but a homogeneous polynomial of second degree. So for example, let us consider 2x square plus 2y square plus 6xy. Now here we can see that every term has total power to be 2. So this is a homogeneous polynomial of second degree. Likewise, we can have 2x square plus 3y square minus z square plus xy minus xz plus 4yz. So here you can see that we have some cross terms also, the cross product terms xy, xz and yz. So this is a quadratic form in three variables. The quadratic forms are usually denoted by capital Q and in bracket they are expressed as the function of the variables which are associated. So the first one is the quadratic form of xy, while the second one can be expressed as the quadratic form of x, y and z. At times we also use another way, so we can have the same expressions, but instead of writing the variable as x, y and z, we can say them to be x1, x2 and x3. So we have 4x1 square plus 3x2 square plus 6x3 square minus x1, x2 plus 4x1, x3 plus 8x2, x3. So this is a quadratic form in x1, x2 and x3. Now once we are given a quadratic form, the next thing which immediately pops up from this part is the associated matrix, also known as the matrix of the quadratic form. The matrix of the quadratic form, it is denoted by capital A and it is a square symmetric matrix of order n, where n is equal to the number of variables in Q, the quadratic form. So in the first case, we can say that Q of xy, it is dependent only on two variables. So the associated matrix A over here is going to be a matrix of order 2 by 2. For the second and third one, the matrix of the quadratic form is going to be 3 by 3. Now let us see how to construct. Since A is a symmetric matrix, we will be needing two kinds of element. One, the diagonals and the off diagonals. Now the diagonal elements are going to be A11, A22 and A33 in case of a 3 by 3 matrix. A11 is nothing but the coefficient of x square, while A22 is the coefficient of y square and A33 is the coefficient of z square. Now, in case the variables in the quadratic forms used is x1, x2 and x3, then a11 is going to be the coefficient of x1 square, a22 will be the coefficient of x2 square, while a33 is going to be the coefficient of x3 square. Keeping in mind the similar strategy, let us talk about the off diagonal elements. So since A is symmetric, we will be having a12 is going to be same as a21, then A13 is going to be same as A31 and A23 is going to be same as A32. Now A12, so you can see that 1 stands for the first variable and 2 stands for the second variable. So the first variable is either xy or it is x1, x2. So this is going to be the coefficient of xy or x1, x2 divided by 2. So in a way, it is half of the coefficient. And likewise, for the next one, A13, so we are interested in the first and the third variable. The first variable is x and the third variable is z. So this is going to be half into coefficient of xz or x1, x3. And likewise, A23, it is related with the second and the third variable. So this is going to be half into coefficient of yz or x2, x3. Now let us quickly write down the associated matrix for the three examples that we have above. So for the first one, since Q is a quadratic form of two variables, the matrix A is going to be of order 2 by 2. Now on the diagonal, we will be looking for the perfect square term. So we have got x square and the coefficient of x square is 2. So the first diagonal entry is going to be 2. Then we have y square, the coefficient over here is 2 again. So the next diagonal entry A22 is going to be 2 as well. Now moving further, we can see that this is xy. So that is the first and the second variable. So it is going to give us A12 entry. And since the coefficient is 6, we are going to split it into two parts. So we are going to write 3 in A12 and another 3 in A21. Now likewise, if we talk about the second quadratic form, now since there are three variables x, y and z, so this is going to be a 3 by 3 matrix. Now again, if you can see, we have x square coefficient to be 2, y square coefficient to be 3 and z square coefficient to be -1. So they form the diagonal elements of the matrix A. Now we have got x, y, the coefficient is 1 and that is associated with the first and the second variable. So that's going to give us the A12 entry and we also got to divide it by half. So it is going to be 0.5 here. And owing to the symmetry of A, the element above 3 is also going to be 0.5. Then moving on to the next element, again you can see it is -1 xz. It is associated with the first and third variable. And since it's -1, splitting it into two halves is going to give us -0.5 over here. And again, owing to the symmetry, we have a -0.5 at A13. Now moving on to the next element. The next element is 4yz. It is associated with the second and the third variable. Splitting it into halves, we are going to get 2 and 2. Now let's move on to the third quadratic form. So again, it's going to be a 3 by 3 matrix. So we have 4 as the coefficient of x1 squared. So the first diagonal entry is 4. Then we have 3 as the next element. And after that, we have a 6. Now coming to the off diagonal elements, you can see this is first and second variable. The coefficient is -1. So the first row and second column entry is going to be -0.5 again. And over here also we'll get a -0.5. Then we have got x1, x3. The coefficient is 4. That means one first row, third element. So the half of that is going to be 2 and we'll get another 2 here. And the last entry is going to be coming from this. So it is second and third variable. So that gives us the second row, third column entry. And the coefficient is 8. So we will get 4 and 4. You could go one step beyond and try constructing quadratic forms in 4 variables and also see if you are able to construct the associated matrix. The next thing we are going to do is we are going to classify these quadratic forms. So the classification of the quadratic form is done on the basis of the eigenvalues of the matrix of the quadratic form. So depending on the eigenvalues of the matrix A, we are going to say what type of quadratic form Q is going to be. So the first type or one of the types is going to be the quadratic form being positive definite. The next one is positive semi-definite. Followed by negative definite. negative semi-definite, and lastly indefinite. So we say that a quadratic form is positive definite if all eigenvalues are going to be strictly positive. So that means that you do not get an eigenvalue which is equal to 0 or get an eigenvalue which is negative. So in case if a matrix is constructed from a quadratic form and you find out its eigenvalues and they all happen to be positive, we are going to say that the quadratic form is going to be positive definite. Now for positive semi-definite, your eigenvalues must be positive and one of the eigenvalues is allowed to be 0. Okay, so means in this case we allow a combination of positive eigenvalues as well as 0. Now for a quadratic form to be declared as negative definite, all the eigenvalues of A must be negative, and if we get that the eigenvalues are negative and one of the eigenvalues is 0, in that case we are going to say that the quadratic form is going to be negative semi-definite. And indefinite is when none of the above four cases are applicable. So in that case you can have eigenvalues to be positive, some eigenvalues to be positive and some eigenvalues to be negative. So if this case arises, we are going to say that the given quadratic form is going to be indefinite. Now let us have a quick example for classification of quadratic forms. So here we have a question to classify the quadratic form, and the quadratic form is of three variables. It is 2x square plus 2y square plus 2z square minus 2xy minus 2y minus 2xz. So the associated matrix or the matrix of the quadratic form is going to be, we are going to denote it by A. It will have order 3 by 3. And let us write down the diagonal entries first. You can see that the coefficient of x square, y square and z square all are 2. So the entries on the diagonal are going to be all 2. And the off diagonal entry is going to be negative 1 coming from xy, negative 1 coming from yz coming over here, and then negative 1 again coming from xz. So we have got the matrix of the quadratic form. And since the problem is classification of quadratic form, what we got to do next is to determine all the eigenvalues of A. So to determine the eigenvalues of A, we are going to take help of the characteristic equation. So the characteristic equation of A is given as the determinant of A minus lambda I is equal to 0. And since it's a 3 by 3 matrix, we can preferably use the shortcut. It is going to be lambda cube minus S1 lambda square plus S2 lambda and minus determinant of A is equal to 0, where S1 is equal to trace of A, S2 is equal to sum of minors. So let's first find out S1. Since S1 is equal to the trace of A, it is going to be the sum of diagonal elements, and that is going to be 2 plus 2 plus 2, which is going to give us 6. Now S2, since it's the sum of minors, let us quickly evaluate the minor. So if I talk about the minor associated with the A11 entry, then the minor is going to be 4 minus 1 plus. Now moving on to the next minor. So if I fix this entry, then again we are going to get 2 2s is 4 minus 1, which will be another 3. And likewise, if I talk about the last minor entry, so you can see again the determinant is going to be 2 into 2, which is 4 and minus 1. So we get 3, 3, 3, 3 times. So S2 is going to be 9. Now the determinant of A is 2 times the 4 minus 1 and then plus 1. I am taking help of the first row, and then here we are going to get the product to be negative 2 followed by minus 1 and then again minus 1, and we'll get 1 plus 2. So you can see that this is going to be 2 into 3 and then minus 3 over here, and again a minus 3. So this is going to be 6 minus 3 minus 3, which is 0. So thus the characteristic equation from equation number 1 is going to be lambda cube minus 6 lambda square plus 9 lambda minus 0 is equal to 0. So you can see only the first three terms are significant, and we can factor out one lambda from it. So we can rewrite it as lambda times lambda square minus 6 lambda plus 9 is equal to 0. And then the quadratic term is nothing but a minus b whole square expression. So this is going to give us lambda minus 3 whole square is equal to 0. And thus simplifying, we are going to get the three eigenvalues to be 0, 3 and 3, or in a way we can write it as lambda is equal to 0 is one eigenvalue, and lambda 2 is equal to 3 is another eigenvalue, but with algebraic multiplicity 2, since it is repeated twice. That's actually not needed in this, but let us just get accustomed to all these kinds of terminologies. Now have a look at the eigenvalues. Now you can see that none of the eigenvalues are negative, since lambda i's are positive or equal to 0. We can come to the conclusion that the given quadratic form is going to be positive semi-definite. So with this, we come to an end to this video. We'll be trying to dive more deeper in quadratic forms and matrix transformation, and we'll be trying to cover up more examples. If you have any suggestions or comments, then you can drop them in the comment. Also, if you have any problems which we can take up, you can put them in the comment section. If you have not yet subscribed to my channel, please subscribe to my channel and also press the bell icon to get notified about the upcoming videos. Thank you so much, and a very happy learning to all of you.